We already know how to project onto a single vector. You drop a perpendicular from B to the line through A, and the projection matrix is A times A transpose divided by A transpose A. Now consider a harder target, not a line but a plane, or even a 47-dimensional subspace inside R100. The line formula breaks down. We need something far more general. Here is the key insight. That same perpendicularity idea, demanding that the area be perpendicular to the subspace, is the only ingredient we need. It produces one single matrix formula that handles every case. From lines to any subspace, one geometric idea does it all. Here is the setup. Matrix A has columns A1, A2, and so on. These columns span a subspace of Rm, the column space of A. Think of it as a plane passing through the origin. Vector B lives in Rm but not in the column space. We want to find the closest point P in that column space to B. Since P must be a combination of A's columns, we write P equals AX hat, where X hat holds the combination coefficients. The error vector E equals B minus AX hat. That's the gap between B and its shadow P on the plane. Geometry tells us that P is closest to B exactly when E is perpendicular to the plane. That right angle is the entire engine of everything that follows. Let's translate perpendicularity into algebra. The error E must be perpendicular to every vector in the column space. Since the columns of A span that space, E must be perpendicular to each column individually. Let's write the conditions one at a time. A 1 transpose times the quantity B minus AX hat equals 0. A 2 transpose times B minus AX hat equals 0. And so on, all the way to AN transpose times B minus AX hat equals 0. Now here's the key insight. Stacking these rows is just matrix multiplication. The rows A1 transpose through AN transpose, stacked vertically, form exactly A transpose. Remember, A has columns, A1 through AN, so the rows of A transpose are precisely A1 transpose through AN transpose. So all of these separate conditions collapse into one elegant matrix equation. A transpose times the quantity B minus AX hat equals the 0 vector. Now distribute A transpose across the subtraction. A transpose B minus A transpose AX hat equals 0. Rearrange by moving A transpose AX hat to the other side. A transpose AX hat equals A transpose B. This is the normal equation. The word normal here means perpendicular. It encodes the geometric condition that the error is orthogonal to the column space. And notice something beautiful. A transpose times E equals 0 means E lives in the null space of A transpose, which is called the left null space. The fundamental theorem of linear algebra tells us this space is perpendicular to the column space. Geometry and algebra agree perfectly. From the normal equation, we now solve for X hat. Multiply both sides on the left by the inverse of A transpose A. This gives us X hat equals A transpose A inverse times A transpose B. These are the coefficients of the projection in terms of the columns of A. Next, multiply on the left by A to get the actual projection vector. P equals A times A transpose A inverse times A transpose B. This is the projected vector in the column space. Finally, factor out B to reveal the projection matrix. Capital P equals A times A transpose A inverse times A transpose. So here are three formulas, each built from the previous one. X hat gives the coefficients, lowercase p gives the projected vector, and capital P is the matrix that sends any vector B to its projection onto the column space of A. All three flow directly from the single perpendicularity condition we established earlier. Let's verify that this general formula reduces to what we already know. Set A equal to a single column vector A, then A transpose. A becomes the scalar, A transpose A, which is just the squared length of the vector. Since it's a scalar, its inverse is simply 1 over A transpose A. Now substitute into the projection matrix formula. P equals A times 1 over A transpose A times A transpose. That simplifies to A times A transpose divided by A transpose A. This is exactly the one-dimensional projection matrix from the previous lesson. So the general formula contains the special case as it should. For a concrete check, let A equal the column vector 1, 1, 1. And then A transpose A equals 1 squared plus 1 squared plus 1 squared, which is 3. And P equals 1/3 times the 3 by 3 matrix, where every single entry is 1. You can verify every entry of P is 1/3. Now let's address the most common mistake students make. A student sees that P equals A times A transpose A inverse times A transpose, and it tries to split the inverse. They write A transpose A inverse as A inverse times A transpose inverse. Then on the left, A times A inverse cancels to give the identity. On the right, A transpose inverse times A transpose also cancels to give the identity. So P equals the identity. That reasoning is wrong. Here's why. The factorization of A transpose A inverse into A inverse times A transpose inverse requires A to have an inverse, but A is typically rectangular, say 3 rows by 2 columns. A non-square matrix has no inverse, so the split is illegal. The only exception is when A is square and invertible. In that case, the cancellation is perfectly valid, and we get P equals the identity. This makes geometric sense. If A is n by n and invertible, then A's columns span all of Rn. Every vector B already lives in the column space, so projecting B just returns B unchanged. Now we verify a defining property. P squared equals P. This property is called idempotency. It means applying the projection matrix twice gives the same result as applying it once. Let's write it out. P squared equals A times A transpose A inverse times A transpose multiplied by another copy of A times A transpose A inverse times A transpose. Now focus on the interior of this product. Right in the middle, we see A transpose A inverse sitting next to A transpose times A. These two factors, A transpose A inverse and A transpose A, multiply together to give the n by n identity matrix. This is because a matrix inverse times the original matrix always equals the identity. So the interior collapses. With the identity matrix in the middle, we are left with A times A transpose A inverse times the identity times A transpose, which simplifies to A times A transpose A inverse times A transpose, and that is just P. Therefore, P squared equals P, confirming idempotency. Geometrically, this makes perfect sense. Once you project a vector B onto the column space, projecting again changes nothing. The vector is already in the subspace. The second key property, P transpose equals P. To prove this, we start by writing P transpose as the transpose of the entire product A times A transpose A inverse times A transpose. Now, recall that transposing a product of matrices reverses the order of the factors. So P transpose becomes A transpose transposed times A transpose A inverse transposed times A transposed. Next, we simplify each factor one at a time. A transpose transposed simplifies back to A. For the middle factor A transpose A inverse transposed, we know that A transpose A is a symmetric matrix, and the inverse of a symmetric matrix is also symmetric, so this factor stays as A transpose A inverse unchanged. And the last factor, a transposed, simply remains a transpose. Finally, we reassemble a times A transpose, a inverse times A transpose. That is exactly our original P. Therefore, P transpose equals P, confirming that the projection matrix is symmetric. Here is the complete picture. One geometric principle, that the error is perpendicular to the column space, produced the normal equation, A transpose AX hat equals A transpose B. From there, we derive 3 key formulas. First, X hat equals A transpose A inverse times A transpose B, which gives us the coefficients. Second, P equals A times A transpose A inverse times A transpose B, which gives us the projection vector. Third, the projection matrix P equals A times A transpose A inverse times A transpose. We also established two key properties. P is symmetric, meaning P transpose equals P, and P is idempotent, meaning P squared equals P. None of this depends on specific dimensions. It works for a line in R3, a plane in R10, or a 1,000-dimensional subspace, and this is far more than abstract algebra. The normal equation powers least squares fitting, regression, signal processing, and nearly every data fitting method in applied mathematics. Next time we put this machinery to work, fitting the best straight lines through data that doesn't lie on any line.